Okay, so the James Webb Space Telescope is challenging our understanding of our cosmic origins. It's challenging what we thought we knew about the very early universe. That is to say, perhaps the first billion years or so after the Big Bang, because what we thought we knew doesn't seem to be borne out by the observations of the James Webb Space Telescope. Now, let's not forget that the James Webb Space Telescope was launched specifically to examine, observe, and give us data from the early universe. And that is its job. That's what it was built for. So it's hardly surprising if what it is showing us doesn't agree with the data that we had before then, because obviously with astronomy, when you have new technology, we always learn something new, and quite often it doesn't agree with what we thought we knew, but that's how science works. So let's first of all have a look at an introduction to this. So the James Webb has given us completely unprecedented views into the early universe. It has gone much further back in time than the Hubble Space Telescope was capable of doing. Its observations are forcing the reevaluation of galaxy and star formation models. It's refining cosmological theories with fresh infrared data. Now, the standard model that we had up until the James Webb Space Telescope looks something like this. So first of all, about 13.8 billion years ago, the Big Bang initiated the expansion of the universe. And after that, we had a very, very, very brief period known as the inflationary epoch, where the universe expanded exponentially. And I worked this out. It expanded something along the lines of, if I remember the figure right, 15 million times the speed of light. Now, if you're going to say, oh, well, nothing can travel faster than light, nothing in the universe can travel faster than light, but there's no such limit on the universe itself expanding that fast. So this took place between 10 to the minus 36 and 10 to the minus 32 seconds after the Big Bang, an unbelievably small period of time during which the universe expanded. And the analogy would be, it would be like taking an atom and expanding it to the size of a basketball in that tiny, tiny time scale. So after that, after the cosmic inflation, which it started for reasons we don't know, and it stopped for reasons we don't know, but all the evidence points to the fact that it did, because if it didn't, we've got lots of questions. And the inflationary epoch, first put forward by the astrophysicist Alan Guth back in the 70s, it answers lots of questions and seems to fit all the models. After that, we had what's called the era of recombination. This is when the first atoms formed, which led to the cosmic microwave background, this wave of radiation that travels across the universe. That is, if you like, the first light released by the universe. Before 380,000 years after the Big Bang, the universe was simply too hot and too dense for light to travel across it. But this suddenly cleared. It was being called the cosmic dawn, and we detect that that microwave radiation today. Since the beginning of the universe, it's been shifted towards the long end of the spectrum to microwave radiation, and that's what we see today. And that cosmic microwave background contains, we believe, the first seeds of the first galaxies, represented by very, very tiny differences in temperature in that radiation of perhaps the millionth of a degree, but that can be and has been measured. So after that, these density fluctuations created the first stars and the first galaxies. The JWST was specifically set up as an infrared telescope. It's able to penetrate dust because it is an infrared telescope. It allows us to see things that are otherwise hidden by dust. And it reveals high redshift objects. In other words, objects towards the edge of the observable universe that are moving incredibly fast. The key instruments are NIRCam, NIRSpec, MIRI, FGS, and NIRIS. Don't worry too much about these, but these are infrared cameras and spectrometers at different near-infrared and mid-infrared wavelengths. And its goal was indeed to observe the first stars and galaxies, what's called the cosmic dawn. Now, one of the things it's discovered is these massive galaxies very early on in the universe's history that were not thought possible to have existed that early on in the history of the cosmos. They are known as the red monster galaxies, and you can see 3 examples of them here. They are mostly sort of formless blobs. They don't have any structure. It was certainly too early for them to form spirals in the case of, spiral galaxies. And what do we know about these? Well, each one of those has a mass of around 100 billion solar masses. So these are getting on for the mass of the Milky Way, and indeed the size of our Milky Way galaxy. And they were formed 12.8 billion years ago. So about 1 billion years after the Big Bang, you had these red monster galaxies. So they obviously formed incredibly quickly. They were very efficient at star formation, converting perhaps 80% of the gas in those galaxies into stars. And when we talk about efficiency, we're basically talking about how much gas in the galaxy as a percentage of the whole is converted into stars. And this completely contradicts what our expectations of early star formation were. We didn't think that the early galaxies would be that efficient at forming stars. So there's obviously something we're not understanding there. And then the discovery of the most distant galaxy, JWST 14-0. And this is that. And you can see in the James Webb image here, it's a tiny, tiny little blob. That's the only way you can describe it in that vast array of galaxies as shown by the James Webb. It was, as we're seeing it, 300 million years after the Big Bang. Very, very early. Well, I know 300 million years is an incomprehensible timescale for humans, of course, but in the history of the universe, it's a very short period indeed. And it has a redshift of about 14, and that basically tells you how far away it is. It shows rapid star formation, but more to the point, it's enriched with heavier elements than we thought could have been forged by stars at that time. So it was producing these heavy elements as a result of supernova explosions much, much earlier than we thought was possible. And this extends the distance record and shifts the formation of the first galaxies backwards, because if we had these structures formed by stars, which obviously formed a lot earlier, only 300 million years after the Big Bang, then there's a problem. There's something we're not understanding about early star and galaxy formation. And then we have the early supermassive black holes. Now, this is a black hole called UHZ1. We have 2 images here. The one on the right is the JWST image, and that shows a little blob, but that's actually a galaxy that hosts the black hole in the image on the left. This is an X-ray image from the Chandra Space Telescope of the black hole itself. Now, this was in existence less than 470 million years after the Big Bang. So we had a supermassive black hole less than 470 million years after the Big Bang. This is a problem. So was it formed from stars collapsing into smaller black holes and then coalescing as we believe happens with at least some of the supermassive black holes? Or was there a giant cloud of molecular hydrogen that collapsed in on itself and under its own weight formed this black hole? We don't know. So more data is needed on that. But it does indicate that there's something we're not understanding about how we can have these supermassive black holes this early in the universe's history. And it does require revision of the early black hole formation models. And there's just a zoomed in image of that black hole in X-ray on the left and the host galaxy that it's at the center of in the JWST image, excuse me, on the right. Then we have the little red dot galaxies. Now, these are plentiful in the early universe. There are lots of them. 6 are shown here, and they're called little red dots because that's exactly what they look like. And what we now think these are young galaxies that have, again, supermassive black holes at their centers that are incredibly efficient at turning gas into stars. And they are compact, they're red, they're what we call AGNs. They have this active galactic nucleus, which is a feeding black hole at the center, feeding on material around it at an astonishing rate. And we've never seen this rate of black holes consuming material this early in the universe's history. And the AGN feedback is likely shaping these galaxies. Well, what do we mean by the AGN feedback? Well, basically what happens is that the wave of radiation, the intense radiation from these supermassive black holes feeding, spreads out through the galaxy. It dissipates gas in the galaxy, preventing the galaxy from forming more stars, acting, as you like, as a throttle on star formation in the galaxy. And these galaxies are likely being shaped by that sort of activity. But we don't know an awful lot about these little red dots as yet. But there are lots of them. I think the Webb has discovered, I think 60 or 70 of this type of galaxy in the very, very early universe. And again, all this poses problems. So to summarize what the JWST has found, unexpectedly mature galaxies less than 500 million years after the Big Bang, suggesting those galaxies formed and matured much earlier than the standard lambda CDM, the lambda cold dark matter model, predicts. So there's something probably wrong with our lambda CDM theory about the early universe and how fast stars and galaxies evolved. You've got high stellar masses and star formation rates. Some early galaxies exhibit stellar masses and star formation rates that exceed theoretical expectations for such young cosmic epochs, implying that these galaxies are much more efficient than forming stars than we had thought possible, or even perhaps that these stars are formed, or the early stars were formed in a way that we're not aware of, that there could be another mechanism for forming these stars that we're just not aware of. That would be absolutely incredible if that turned out to be the case. You've got compact high-density structures. Many of the earliest galaxies appear extremely compact and dense, challenging models of gradual hierarchical assembly via mergers and slow gas accretion. What does this mean? Well, the way generally that we think galaxies get to grow so big is by consuming smaller galaxies, as in the case of our own Milky Way galaxy. So galaxies come together to form bigger galaxies, which then get eaten by bigger galaxies in a sort of a hierarchy. And it could be that we've got this wrong, that there could be other mechanisms at play there that we're just not aware of. You've got irregular morphologies and dynamics. As you've seen, some of these early galaxies are sort of irregular, clumpy or disk-like structures. These are not at all how we expected them to be in terms of their shape and their morphology. There may be other mechanisms at play governing the shape and morphology of these galaxies that we're just not aware of at the moment. And also, of course, we shouldn't leave dark matter out of this. As you may know, most galaxies are surrounded by a halo of dark matter, and what we're seeing from the James Webb indicates that these halos formed much earlier than expected. We may need to revisit the model of dark matter behavior in the early universe as a result. So how do we fix all this? These are the problems with what the James Webb has shown us. What might be the fixes for solving these cosmic conundrums, if you like? Well, obviously, we need to revise our galaxy formation timelines. We may need to account for galaxy formation within 200 to 300 million years after the Big Bang, much earlier than our current models predict. And what this implies is a more rapid collapse of gas into dark matter halos and faster onset of star formation. So the dark matter halos may have formed much earlier, and the stars may have also formed much earlier and formed these galaxies. We may have to rethink our star formation efficiency. Models must incorporate much higher star formation efficiencies in early galaxies, suggesting that primordial gas cooled and condensed into stars more effectively than expected, possibly due to enhanced turbulence, different feedback processes, or altered initial mass functions. So there's a lot to think about with how we view the formation of these early stars. Our models of dark matter halos may be wrong. By the look of it, what it is suggesting is that our lambda CDM models may need refinement to permit the earlier emergence of more massive dark matter halos, potentially requiring modifications to small-scale structure growth rates or reconsideration of the whole warm versus cold dark matter scenarios. So that's another thing that needs looking at. Accelerate chemical enrichment mechanisms. Well, as I said earlier, some of these galaxies have got much heavier elements in them than should have existed at that time, because don't forget, heavier elements are created by successive generations of stars. And that implies that the population 3 stars, I know this is confusing, but the first generation of stars are actually called population 3 stars. They were supermassive stars. Perhaps they formed and died more rapidly than we think, or that these early galaxies experienced much more intense starburst activity and supernova-driven mixing of these gases and elements much earlier on than we thought, but we don't know what might be the mechanism for that. And we need to look at our models of galaxy growth. Once formed, how do galaxies grow? And what the James Webb is showing us is that there's much less chaotic growth than expected, that there is order appearing in the structure of those galaxies much earlier than we thought. And there we are. So we also need to incorporate non-standard initial conditions. May imply that initial density fluctuations, the one I talked about that you can see in the cosmic microwave background, were more pronounced or differently distributed than predicted by inflationary models. So even the inflationary model has to come under scrutiny to understand what the hell's going on here. And there we are. So to fix all of these problems needs looking at a lot of ideas that we thought were correct. As you can imagine, this is not going to be an easy task. Fixing all this is not going to be easy, because it means looking at a lot of things and a lot of scratching of heads, and a lot of new ideas need to come up.